This is chapter 15 from Master Math Mentor's AP Calculus AB manual. It discusses continuity and differentiability. In the first video, part one, we'll be going over continuity of a function. In the past, we've talked about continuity as being you can sketch the graph without lifting your pencil. That's very formal. That's not quite accurate. For instance, f of x equals x squared graphs a parabola, and that parabola is continuous. But is it really possible to draw the entire graph without picking up your pencil? The answer is no. It's really not possible to draw the entire graph. So we need a more formal definition, and that's where calculus comes in. And this idea of limits is going to help us talk more about continuity of a function. So a function f is continuous at some point c. All three of these have to be true, not just one of them, but all three. The limit as x approaches c of f of x has to exist. So it has to equal some number. F of c also has to exist. And number one and number two have to be equal. So the limit as x approaches c of f of x has to, in fact, equal f of c. What this really says is, number one, as x gets closer and closer to some value c, both from the left and the right, we do approach a limit, L1, some number. The function is defined at x equals c and is equal to some number. And those two numbers, in order for this to be continuous, those two numbers have to be equal. If a function is continuous at all values of x, then we say that that function is a continuous function. And we'll talk more about continuous functions in a little bit. So let's look at some graphs. A function could be continuous in some parts of its domain and discontinuous in others. So let's look at some graphs here and see if we can determine if these are continuous at the x value indicated. So what we need to do, we need to show three things. We need to show the limit as x approaches, in this case, 1 of f of x. What would that equal? Well, in this case, if we look at the right-hand side would be this number. The left-hand side would be this number. And since those don't match, the limit in this case doesn't exist. And since the limit doesn't exist, we can say this graph, f of x, is discontinuous or not continuous at x equals 1 because the limit doesn't exist. All right, looking at part B, the limit in this case does exist. The limit as x approaches 1 of f of x, that does exist. That does exist. We don't know exactly what that y value is in this case, but that doesn't matter. That does exist because the left side and the right side are approaching the same value. But what does not exist, this idea of f of c, what is f of 1? What is f of 1 equal to? And in this case, f of 1, looking at that graph, f of 1 doesn't exist. There's no closed dot. There's an open dot at x equals 1, but there's no closed dot anywhere else. So since f of 1 doesn't exist, this is not continuous at x equals 1. Looking at part C, here is part C. Does the limit as x approach 0 of f of x exist? The answer to that is yes, because here is our value. It's going to be approaching the same from the left and right, so that does exist. Does f of 0 exist? The answer to that is yes. It's going to be equal to this value. And since the limit and f of 0 exist and they're equal, so in this case, we can say, even though we don't know exactly what that number is, we can say that the limit as x approaches f of x is equal to f of 0. So since the limit as x approaches 0 of f of x is equal to f of 0, we can say that this function is continuous at x equals 0. Part D, the same is true for part D. Looking at this, we see that the limit does exist. We see that f of c does exist. I'm not going to write all that out again, But we see that that is true. So this function would be continuous at x equals 0. All right, moving on, looking at part E. If we look at part E, we want to know, is this continuous at x equals 2? So it should be pretty obvious that it's not continuous at x equals 2. We approach the asymptote here, we approach the asymptote here. So the limit doesn't exist. And since that limit doesn't exist, our function is not continuous at x equals 2. All right, part F. We are approaching the same positive infinity, but in this case, the limit as x approaches 2 of f of x does not exist. And since that limit doesn't exist, our function is not continuous at that location, even though it does equal a positive infinity. We talked about before, when limits equal infinity, they technically don't exist. Over here on part E, I failed to mention this a second ago, but f of c also does not exist. All right, if we look at part G, notice that this point right here might be what you're interested in, but in this case, that's actually not what we're interested in. We're interested in x equals -2, so about right there. And if we're looking at -2, the left and right-hand sides approach the same value. That function is defined at that point, and the limit as x approaches -2, the limit as x approaches -2 of f of x is equal to f of -2. Therefore, we can say the function is continuous at x equals -2. All right, part H, we see that the limit here is approaching, the left-hand limit is approaching this. The right-hand side looks like it's going up to infinity. So since the limit as x approaches -1 of f of x does not exist, we can say that that function is not continuous at x equals -1. All righty, moving on. This next part just gives us some definitions. Example A is a step discontinuity. Step discontinuity, because if you notice, you have to step from here to get up to the next level. So you got to kind of step from here to get up here, kind of a step. Example B is an example of a removable discontinuity. We normally call that a hole, and that's the word we've been used. It's like that point has been removed from the graph. This right here in part G, that would also be a removable discontinuity. And we'll see why it is called removable discontinuity when we look at this in algebraic form. So here's a table. They just tell us some things about algebraic form. We can make the following conclusions. All polynomials are continuous for all values of x. And the reason that that is because the domain for a polynomial is -infinity to infinity. You can plug any number in for x and get a number back out. So it's going to be continuous. If we look at fractions where you have like a x in the numerator and an x in the denominator, we don't want the denominator to be equal to 0. So wherever the denominator is equal to 0, that's going to create some type of discontinuity. It makes no difference if it cancels out or not. If it does cancel out, that's when we get a hole. If it doesn't cancel out, it's going to be a vertical asymptote. Part C, odd roots are continuous everywhere. The reason being, the domain again there would be -infinity to infinity. You can take the odd root of a negative number. For instance, the cubed root of -8. What can we multiply by itself 3 times to get -8? And that would be -2 times -2 times -2. And if we multiply those together, we do get -8. But if we're looking at an even root, this is not true. We can't take an even root like square root of -4. We can't take that. This is this idea of imaginary numbers. So if we ever have an even root, we need the number under the radical to be greater than 0. So it's going to be discontinuous whenever that number is less than 0. Sine and cosine are continuous everywhere, and exponentials are continuous everywhere. Again, the reason behind that, you can take any number you want and plug in for x, negative infinity to infinity, and you will not get any type of domain error. The two main domain errors we get are imaginary numbers, or division by 0. And when we have those two things, we may have some type of discontinuity. Otherwise, it's going to be continuous everywhere. All right, part A. Looking at part A, we see that part A is a polynomial. So polynomials are continuous everywhere. Part B, we want to know, find any points of discontinuity. We have a fraction, and we cannot divide by 0. So this x minus 1 cannot equal 0. So if we were to set that equal to 0 and solve for x, we add 1 to both sides, so we get x equals 1. So if we were to graph this, this would probably be a hole at x equals 1. So it would be discontinuous at x equals 1. Part C is an odd root. It doesn't matter if the number under that root is positive or negative. So part C is going to be continuous everywhere. Part D, however, is an even root, and even roots cannot be negative. So if we're trying to figure out where this is discontinuous, this is going to be discontinuous where x squared minus x minus 6 is less than 0. So any number that we plug in and get a number out that's less than 0 is going to make this function discontinuous. In order to solve this inequality, we need to factor. We get x minus 3 times x plus 2 is less than 0. We need to solve both of these for x. Essentially, we get x equals 3 and x equals negative 2. Now, in order to solve this, it would probably be a good idea to draw a number line. We're going to put negative infinity way over here. We're going to put positive infinity over here. We're going to put negative 2 on this number line, and we're going to put 3 on this number line. And then we can pick a number between negative infinity and negative 2. So let's pick a number like negative 3. We're going to plug negative 3 back in right here and see if it satisfies that inequality. We don't really need to worry about the numbers, just the sign, since we're looking at 0. So negative 3 minus 3 is a negative number, so we get a negative number. And negative 3 plus 2 is also a negative number. And negative times negative is equal to a positive number. Is a positive number less than 0? And the answer to that is no. A positive number is not less than 0. If we pick a number between negative 2 and 3, the easiest number to pick is probably 0. 0 minus 3 is a negative number, so call that negative 1. I know it's negative 3, but the number doesn't matter. 0 plus 2 is a positive number, and a negative times a negative, or a negative times a positive, is a negative, and is a negative number less than 0? And the answer to that is yes. So here we get positive numbers between negative infinity and negative 2. Here we get negative numbers between negative 2 and 3, and between 3 and infinity. What do we get between 3 and infinity? Let me make this look a little bit nicer. And we're just going to put the signs here instead of putting yes or no. So between negative infinity and negative 2, any number you pick between negative infinity and negative 2, it's going to give us a positive number. If we plug in negative 2, we're going to get 0. Any number between negative 2 and negative 3 is going to give me a negative number. And if we pick 3, we get 0. Then let's pick a number between 3 and infinity. That number might be 4. If we plug that in, 4 minus 3 is a positive number, and 4 plus 2 is a positive number. And a positive times a positive is a positive. So we're looking for where this is less than 0, and it's going to be less than 0 between negative 2 and 3. So our function would be discontinuous on the interval negative 2 to 3, not including negative 2 and not including 3. So that's why we use parentheses instead of brackets. Part E, cosine is continuous everywhere, but we have a fraction x minus 2, and we can't divide by 0. So where would that be equal to 0? that would be equal to 0 at 2. So we would be discontinuous. This function would be discontinuous at x equals 2. Part F, e to the negative x, we're going to make that a positive exponent. We get 1 over e to the x minus 1. We do have a fraction here, so we would look at this idea of when is e to the x equal to 0. And the answer to that is never. The short way to explain this is just to pick a couple examples. We get e to a positive power. Well, that's clearly going to be equal to a positive number. If we get bigger than 0, we get e to a negative number. That's just going to be 1 over e squared, which is still not 0. It's still actually a positive number. So in short, e to the x can never equal 0. And since e to the x can never equal 0, our function in part F would be continuous everywhere. So when we talk about continuity, continuity is really just a reach of domain. So a lot of these just go back to this idea of the domain. When we look at piecewise functions, typically, sometimes piecewise functions could be continuous everywhere with each piece, but we need to check the piece where the rule changes. So we're going to be doing those 3 things that we wrote down at the beginning of class. We're first going to find the limit as x approaches that number of f of x. We're going to find f of that number, and then we're going to check to see if those 2 things are equal. So if you remember from chapter 5, this is a good review from chapter 5. How do you find the limit of piecewise functions? We have to look at the left side, and we also have to look at the right side, and our rule changes here at 1. So the left side would be the top. In this case, x is less than or equal to 1. So we're going to plug 1 into that. So we get 1 squared minus 3. 1 squared minus 3 is negative 2. The right side would be this bottom piece, 1 minus x. So we're going to plug 1 into that. 1 minus 1 is equal to 0. I don't have to do anything else after that because since those 2 don't match, we know that the limit as x approaches 1 of f of x does not exist. And if it does not exist, we also know that this function is not continuous at x equals 1. It might be, and it actually is continuous everywhere else, but they didn't really ask for that. They only asked for where the rule changes, and the rule changes at x equals 1. Number 4, same idea. We're going to find the limit as x approaches 2 or negative 2 from the left, and the limit as x approaches negative 2 from the right. So the left side would be less than negative 2. So we're going to plug negative 2 in there. We get negative 2 squared plus 3 times negative 2 minus 2. That would be equal to 4 minus 6 minus 2. 4 minus 6 is negative 2. And negative 2 minus 2 is negative 4. The limit as x approaches negative 2 from the right, we're going to use this side. That would be negative, parentheses, negative 2 squared. We've got to be careful here. That negative right there is actually not being squared, so it needs to go outside the parentheses. So we're going to square negative 2 first. So negative 2 squared is 4, and then we're going to multiply that by the negative outside, which is negative 4. So what do we see? We see that the left and right hand limits align and are exactly the same. So the limit as x approaches negative 2 of f of x is equal to negative 4. We also need to find f of negative 2. In order to find f of negative 2, we're going to pick out the one where it says equal to. And in this case, it's equal to in the top one. So we're going to plug negative 2 into the top function, which we've kind of already did. I'm just going to write it down, but typically I wouldn't write all this out because we literally did this in that first limit for the left-hand side. But we do know that that equals negative 4. And since these two are equal, the limit and f of negative 2 are equal, we were to put this in words. We talked about explaining our work with our free response questions. since the limit as x approaches -2 of f of x equals f of -2, I know I ran out of room there, but that's the idea, then f of x is continuous at x equals -2. All righty, roll on. You can do 5 and 6 right quick. Same idea. X is less than or equal to -1. So that's going to be our limit piece for the left side. X, I don't need that one there, just the minus sign. So we're going to plug in -1. We get 3 raised to the -1, which is 3 to the +1, which is just 3. And the limit as x approaches -1 from the right side, we're going to use this bottom function. We get 1 over 1 plus 1, which is 1/2. And 3 and 1/2 don't equal. And since that limit doesn't exist, man, we don't get 1 over 1. My bad. This should be a -1. Y'all let me slip up. We get 1 over -1 plus 1, which is 1 over 0, which doesn't exist. Either way, we end up with the same conclusion, that the limit doesn't exist. So the limit as x approaches -1 of f of x does not exist. Therefore, f of x is not continuous at x equals -1. All right, let's see if we can knock out number 6. X doesn't equal 4. So this is going to be the left and the right-hand side. So we're looking at something where we're going to use this top function for everything, and we're only going to use the bottom function when x equals 4. So we can take the limit as x approaches 4. We don't really need to worry about the left and right-hand side because they're going to be the same this time, of x minus 4 over x squared minus 16. If we were to try to plug in 4, we get 4 minus 4 over 16 minus 16, which is 0 over 0. And if that happens, we want to factor and cancel. So we get the limit as x approaches 4, x minus 4 over x squared minus 16 is x plus 4 times x minus 4. We can cancel out the x minus 4s. So we get the limit as x approaches 4 of 1 over x plus 4. Now, if we plug 4 in, we get 1 over 8. 1 over 4 plus 4 is 8. So the limit does exist. It equals 1 over 8. So when x equals 4, we're going to use this bottom piece now to help us find f of 4. So we plug in 4, we get 1 over 3 times 4 minus 4. That's 12 minus 4, which is 8. And since the limit is equal to the function value, then we know that our function is continuous at x equals 4. Continuous at x equals 4. Find the value of the constant k that will make the function continuous at the location of the rule change. So what we know, if it's going to be continuous, we know that the limit as x approaches this value has to equal f of that value. So what we're going to look at, the left and right hand limits in this case, we're going to set them equal to each other. The limit as x approaches 1 from the left of f of x has to be equal to the limit as x approaches 1 from the right of f of x. Well, the left-hand piece is going to be this piece right here. So we get 3 times 1 plus 2, and that has to be equal to the right-hand side. The right-hand side, which is 2k minus, we're going to plug 1 in for x, 2k minus 1. And then we're going to solve for k. We get 3 plus 2 is 5, equal to 2k minus 1. We add 1 to both sides. We get 6 is equal to 2k. And divide both sides by 2. 6 divided by 2 is 3. So in order for this function to be continuous at x equals 1, k must equal 3. Part B, part C, similar. We're going to do the same thing. I'm not going to write this. I guess I will. The limit as x approaches 2 from the left of f of x has to equal the limit as x approaches 2 from the right of f of x. So we're going to plug 2 in for x. So we get k times 2 squared has to equal k times 2 minus 6. So we did the left side and the right side, left and right. So we get 4k is equal to 2k minus 6. We can subtract 2k from both sides. 4k minus 2k is 2k. That equals negative 6. Divide both sides by 2, and we get k is equal to negative 3. And we are rolling into part C. This will be the last part of this video. We're going to plug 1 in for x and 1 in for x, and we're going to set those things equal to each other. So we get k squared minus 12 times 1 is equal to k times 1. We get k squared minus 12 equals k. We have a quadratic, so we're going to get this equal to 0. K squared minus k minus 12 is equal to 0. At this point, we can factor. What can we multiply to get negative 12? That adds to give me negative 1. That'll be k minus 4 and k plus 3. So we're going to get 2 values of k this time. We're going to set each of those equal to 0 and solve for k. So we get k equals positive 4 and k equals negative 3. That's going to do it for this video. In part 2 of this chapter, we will go over what it means to be differentiable. That's got to take this idea of the derivative into effect. If you have any questions, I will try to get back to you as soon as I can. Hope you have a good day. Hope you're having a good time in school.